Welcome back to this next video in which we are discussing separable polynomials over a finite field of characteristic equal to a prime. Okay, so what we are trying to prove then is Theorem 1, that if you have a polynomial which is irreducible in the ring of polynomials over our finite field of characteristic P, then that polynomial is separable over the finite field of characteristic P. Okay, and we've shown that all of this hinges on us being able to conclude that the derivative of this polynomial is not equal to 0, and we have not so far given an argument as to why that is true. We know that it's going to be true if we're working in a field of characteristic 0, but we're not. We're working in a finite field of characteristic P, so we need to come up with some other argument. Okay, so here is going to be an intermediate little theorem, if you like. So we might call this a lemma. Okay, so we'll have a little lemma here. Okay, so of course the lemma is just going to be that the derivative of this polynomial is not equal to 0 if the polynomial is irreducible. Okay, so if you take some polynomial p of x that is irreducible, so I should put if p of x is irreducible in the ring of polynomials over a finite field of characteristic P. Okay, I won't write all that down because it'll take too long. So if p of x is irreducible in the ring of polynomials over a finite field of characteristics P, I'll just put in the ring of polynomials here, then the claim is that the derivative of this polynomial does not equal 0. So the derivative of p of x is not equal to 0. That's the claim, and of course if we can prove that, then we've proven Theorem 1. Okay, so what we're now going to see, of course, is the argument as to why this is true, and it's not too difficult, but it is substantially more complicated than the argument as to why this was true when we had a field of characteristic equal to 0. Okay, so this argument is going to absolutely hinge upon us having a decent understanding of something called the Frobenius Endomorphism. Now, the Frobenius Endomorphism is something that I discuss in the playlist on ring theory. There's an entire video dedicated to the Frobenius Endomorphism, and if you've never seen the Frobenius Endomorphism before, I advise that you go and watch that, because as I say, this argument is totally going to hinge on it. Okay, if you have seen it before, then I'll just give you a little bit of a reminder about what it is now. Okay, so this is going to be the Frobenius endomorphism. So remember, the Frobenius endomorphism is an endomorphism that you can use for any ring of characteristic equal to a prime. So it doesn't need to be a field that we're applying this to, and that's going to be important. We're actually going to apply this to a ring in a moment as well as just the field. We're going to apply it to two separate algebraic structures. Okay, so it's important that we know that it operates over an arbitrary ring. Okay, so we're going to have some ring that has characteristic equal to a prime. That is important. Okay, it doesn't work over an arbitrary ring. It does need to be a ring of characteristic P. It operates over some arbitrary ring of characteristic equal to P. Okay, and the Frobenius endomorphism then is of course an endomorphism which is a homomorphism from the ring to itself. So it's a mapping that sends all of the elements of the ring onto other elements of the ring, and it's a mapping that actually obeys the axioms of a ring homomorphism, i.e. additive compatibility, multiplicative compatibility, and the fact that the multiplicative identity is sent onto the multiplicative identity. And the way this mapping works is that it takes any arbitrary element of the ring, which I'll just call A here, and maps it onto A to the power of P, where of course P is the characteristic of our ring, the prime that is the characteristic of our ring. Okay, and as I say, we show in the video on the Frobenius endomorphism, and I'll just write the name in case you don't know how to spell it. So this is called the Frobenius, like so, endomorphism. Okay, so an endomorphism is just a ring homomorphism where the domain and codomain are the same ring. Okay, so it's just a fancy word, another piece of terminology meaning a special map from the ring to itself. Okay, right, and we saw in the video on the Frobenius endomorphism that indeed this map, if we're working in a ring of characteristic equal to this prime, this map does obey the axioms of a ring endomorphism. Now, multiplicative compatibility and the fact that the multiplicative identity is sent onto the multiplicative identity, they're very trivial, they're absolutely pips to show, they're obvious from just the definition. The one that is not obvious and took us quite a while to actually prove in the video on the Frobenius endomorphism is additive compatibility, that if you take an arbitrary A and B from your ring and take phi of A plus B, that it's equal to phi of A plus phi of B. Now, writing out explicitly what phi does to A plus B, this is that A plus B, in the ring of course, capital R, to the power of P is equal to phi of A, which is just A to the power of P, plus phi of B, which of course is just B to the power of P. Again, just looking at that, you know, it doesn't look as though that would be true at all, but it turns out that it is true, provided that we are working in a ring of characteristic equal to a prime. Okay, and that's the incredible result that really we're going to make use of for this proof. Okay, now I'm not going to prove this result here because it took about 20 minutes, but I'll just give you a little the little highlights of the proof, so that those of you who have seen it will just remember why this is true. So remember, the way that we did this, the way that we proved this, is we expanded this with the binomial expansion, and then we found that if we were working in a ring of characteristic equal to a prime, that all the middle terms, so all the terms in between the two most extreme terms here, they would all be equal to 0 because they'd all have a coefficient that was a multiple of p, and of course because we're working in a ring of characteristic equal to p, those are all going to be equal to 0. So that is a little sort of brief few lines to summarize why that is actually true. But as I say, if you want to see the more in-depth explanation as to why that is true, do watch the video on the Frobenius endomorphism. Okay, so the Frobenius endomorphism then is this endomorphism that you can apply to any arbitrary ring of characteristic equal to a prime. Okay, provided of course that you do use the same prime here in the definition of the Frobenius endomorphism that is the prime that is the characteristic of the ring. Okay, right. Now this is beautiful, even more beautiful, when you apply it to fields, and in particular when you apply it to finite fields. And what are we working with? We're working with a finite field of characteristic equal to p. Okay, so this is going to be very interesting. So, if you apply it to an arbitrary field of characteristic p, so not necessarily a finite one initially, okay, so I've just got some arbitrary field of characteristic equal to p. Now, of course, a field is a ring. It's a very special ring. It's a non-zero commutative ring in which all non-additive identity elements have a multiplicative inverse, but it is just a ring, so you can certainly build the Frobenius endomorphism here. But the beautiful thing about doing it with a field is that fields have a very simple ideal structure. They only have two ideals. They have the zero ideal and the unit ideal. So that means that the kernel of this ring homomorphism, because of course a ring endomorphism is a ring homomorphism, has only two options for it. It can only be equal to the zero ideal or the unit ideal. Now it's not equal to the unit ideal because we know that 1 is sent onto 1. Okay, so it's not sent onto 0, so it cannot be the unit ideal. So that must mean the kernel of this homomorphism is the zero ideal, and therefore we know that the ring homomorphism here will be injective. Okay, so we know that it's injective as soon as we're working with a field of characteristic p. Now, if you're working with a finite field, so if now this field is finite, then of course you know that whenever you've got an injective map from a set to itself, then that's going to and that set is finite, that it's going to have to be a bijective map. How could it not be? Okay, if every element here has to go to a distinct element over here, well, there's only a finite number of elements here and a finite number of elements here, and they're the same number. Okay, so if everyone here has got to go to something different here, then everything here is going to be hit, so the map is surjective. So if we are working with a finite field of characteristic p, then we can define the Frobenius endomorphism from this field to itself, and it will be a bijective map. In particular, it will have an inverse. Okay, and this is going to be extremely important. So what this means is that if you take any element from your field, so you give me any, let's say, little a from the field, I can find you there exists some b which is an element of the field, such that if I raise b to the power of p, i.e. if I take phi of b, I hit a, and that's because this map is surjective. Okay, I'm effectively just saying b is the inverse of a under the Frobenius endomorphism. All elements in the field have an inverse. They can be written as some element to the power of p, and that's incredibly powerful, and that's what we're going to need to know in the proof of this lemma here. Okay, so there's just a little bit of a reminder of the Frobenius endomorphism and the power of the Frobenius endomorphism when applied to a finite field of characteristic equal to a prime. Okay, so now back to this statement then. So what we're going to do is we're going to consider what must this polynomial look like if the derivative is equal to 0. Okay, well actually, sorry, let me just go back a few steps and tell you my approach to proving this. So this was just the sort of prerequisite knowledge. This was what we need to know in order to prove this. But now let me tell you my actual strategy for proving this. So I'm going to prove this by contradiction. We're going to assume that p of x is indeed irreducible, and then what we're going to assume is that the derivative of the polynomial is equal to 0, the exact opposite of what we want to prove, and we're going to arrive at a contradiction, and the contradiction is of course that p of x is not going to be reducible. Sorry, it's not going to be irreducible, it will be reducible. Okay, so what we're going to start off with then is the assumption that the derivative of the polynomial is equal to 0. And what I want to consider is what will the polynomial have to look like if indeed the derivative of the polynomial is equal to 0. Well, which polynomials in the ring of polynomials over a finite field of characteristic equal to a prime, in fact, it doesn't necessarily need to be a finite field, just a field of characteristic of prime, are actually going to have derivatives equal to 0? Well, it's only going to be those polynomials where the non-zero coefficients are only in front of powers of x that are multiples of p. Okay, so if this is true, then I can make a conclusion about what this polynomial looks like. It will look like this. It might have a constant term, which I'll call p0 here. Then it will have, let's say, p1 in front of x to the power of p. Okay, plus maybe p2 in front of x to the power of 2p, and it will go on like this. So it might go up to p, let's say, m, x to the mp here. Okay, so I hope you understand what I'm saying here. If the derivative of the polynomial in this ring of polynomials over the field of characteristic p is going to be equal to 0, then that means that all of the coefficients which are non-zero must be in front of powers of x that are a multiple of p. If you had some non-zero coefficient in front of a power of x that was not a multiple of p, then when you took the derivative of this polynomial, you'd end up with that term still remaining non-zero, so you wouldn't get 0. Okay, so the instant we know that the derivative of the polynomial is equal to 0, it means that the polynomial looks like this, i.e. a silly polynomial where all of the powers of x that have non-zero coefficients are these multiples of p. And then of course when you differentiate this, the constant term will go and all of these will go as well, because you'll be multiplying the coefficients by multiples of p, which are of course 0 in our field of characteristic p. Okay, where to now then? Okay, so we're going to play around with this. Now remember, all of these pi's, they are elements of my finite field of characteristic p here. Now what have I just said about a finite field of characteristic p? That the Frobenius endomorphism exists there and that it is bijective. So what I can do for each one of these is I can write it as some other element of the field, let's say ai to the power of p, where ai is just going to be the inverse of the Frobenius endomorphism, phi inverse applied to pi. Okay, so for each one of these, p0, p1, p2, all the way up to pm, you can find an ai, an a0, a1, all the way up to am, such that this is true, that when you raise it to the power of p, you get the corresponding pi. Okay, so for each one of these you can do that. Because of the fact that the Frobenius endomorphism is bijective when applied to a finite field of characteristic p. So what that now means is that I can rewrite my polynomial p of x like so. So it'll now be a0 to the power of p, okay, plus a1 to the power of p, and of course this at the moment, I want to stress, this at the moment is an operation in the finite field of characteristic p. Okay, you can, if you like, view it as an operation in the ring of polynomials over the field capital F, because of course the field is contained within that if you wish. But if you, in a way, it's more logical just to think about you have to manipulate this to turn it into the correct coefficient that you're then sticking in front of the power of x. Okay, but we will change our meaning in a moment, and I'll skip out this term just to save paper, or save ink. Okay, so then we'll get plus am to the power of p, x to the mp here. Okay, so all I've done is rewritten the coefficients in this way, where you've just now got these other elements of the field, and you have to firstly multiply them by themselves p times to actually turn them into the appropriate thing. Now, here comes the clever bit, and I want you to understand what we're doing here. At the moment, this is a polynomial in the ring of polynomials over the finite field of characteristic p. And as such, it is a cold, hard symbol. Okay? It is a bunch of coefficients from the field capital F in front of these placeholders, which are these powers of x, and then separated by these plus symbols, but that is all it means. It is the symbolic meaning of the polynomial. Okay, we are about to change over to using a different meaning here. Okay, so what I'm now going to do is write it like so. It's going to be a0 to the power of p plus a1 times x to the power of p plus all the way up to am times xm to the power of p. But understand the scale of the jump that I have made here. Okay, I've changed the meaning completely. This is no longer actually the final answer. This now is something that you would have to work out in the ring of polynomials over the field capital F to actually get a final answer. Because now these additions, they've gone from just being the cold hard symbol form to actually being additions in the ring of polynomials over the field. Okay? These are the elements of the actual ring of polynomials over the field. These are the polynomials now. So I've got a polynomial here which is just a0, that's an element in here. I've got a polynomial here which is just a1 times x, that's an element of this. All the way up to this one here, am times xm, that's a polynomial here. They're very simple polynomials because they've only got one term that's non-zero, but they are still polynomials. We've then got all of them raised to the power of p, and that is done in the ring of polynomials over the field capital F. So, of course, this is a ring, it's got addition and multiplication defined on it, so I can take this polynomial and multiply it by itself p times in this ring of polynomials over the field capital F. So understand how much the meaning has changed here. I have decomposed it in this incredible way. This was an actual polynomial. This is not. This is loads of polynomials with operations applied to them that you could work out in principle. You could work all of this out to get a final answer. And hopefully you agree that if you did work this all out, what would you get? You'd get this. Okay? So it's another way of writing it, but I have decomposed it completely into this form that requires you to do loads of operations to actually get the final answer. So this is not an actual element of this set. This is loads of these little elements of the set, this one, all the way up to this one, with operations applied to them in this ring, and if you applied all of those operations, you would then get the final answer. So understand the scale of how much I've changed it there. Okay, and now what's my next move going to be? Well, what I'm going to do is now say, let's apply the Frobenius endomorphism to the ring of polynomials over this finite field of characteristic equal to a prime. So there will exist a Frobenius endomorphism for the ring of polynomials over the field, the finite field of characteristic p. Okay, and what we know is that whenever you take a ring of polynomials over a certain ring here that has characteristic equal to a prime, the characteristic of the ring of polynomials will be the same as the characteristic of the coefficient ring. Okay, that you don't need the actual ring to have characteristic of prime. That holds more generally. If you've got a ring and you take its ring of polynomials, then the ring of polynomials will have the same characteristic as the original coefficient ring. That's very easy to see because, of course, if the multiplicative identity in here is exactly the same as the multiplicative identity in the initial coefficient ring. So we are using the fact here that the characteristic of the ring of polynomials over a coefficient ring is equal to the characteristic of the coefficient ring. Okay? So what this means is that if we consider the characteristic of this ring of polynomials over the finite field of characteristic P, then of course the characteristic of this ring of polynomials is equal to P. So the characteristic of f adjoin x here is equal to P, i.e. it's a prime. So we've got a ring here with characteristic equal to prime, so we can apply the Frobenius endomorphism. Now note, this is a ring, not a field, so it's not going to be as beautiful as it was in a field, but it's still going to be an endomorphism, i.e. it's still going to obey additive compatibility, multiplicative compatibility, and the fact that the multiplicative identity is mapped onto the multiplicative identity. Now which of those do I need? I need additive compatibility here. Look what I've got here in my ring. I've got loads of the elements of the ring raised to the power of p. Okay, if I liked, I could write this as the Frobenius endomorphism for this ring of polynomials applied to a0 plus the Frobenius endomorphism applied to this polynomial a1x, and of course the addition here is in the ring of polynomials, and you could go on plus all the way up to the Frobenius endomorphism applied to am xm, like so. Nothing wrong with what I've just done there. Okay, those are exactly the definitions of the Frobenius endomorphism applied to these polynomials. You just raise it to the power of p in the ring that you're working with. Okay, and now we use the fact that additive compatibility holds true, okay, to say that this is going to be phi of, add them together first, so a0 plus a1x plus all the way up to am xm, where all of these are going to be added together in, of course, the ring of polynomials over the field capital F. Okay, and now what's this going to be equal to? Well, just apply the definition. This is just going to be this polynomial a0, and now let's go back to the cold hard meaning. So this is in its monomial decomposition at the moment. Okay, it's actually this polynomial plus this polynomial plus this polynomial, but we know what's the answer to that going to be. We'll revert back to the cold hard symbolic meaning. This is the actual element of this set, okay, which is the answer to all of this. So these pluses are now no longer additions in here. They are the cold hard symbols. This is a symbol now in here. But of course, what do we need to do? We need to raise this to the power of p. Okay, so this is one polynomial in here. And I know previously I underlined polynomials in green, but this one I'll underline in orange to denote the fact that the additions are these cold, hard symbols in between the terms. So this is one polynomial now, rather than loads of polynomials added together. So that's how I've changed the meaning here. Okay, it is, you know, implicit. Implicit isn't the right word. It's not. You know, it's easy to miss if you don't have it completely pointed out, but these are important little changes in my opinion. Okay, so you've got this polynomial now in the ring of polynomials over the field raised to the power of p, and of course, what is this that we've got here? Well, this is just our polynomial p of x. So I've now got p of x written as this polynomial, which is in the ring of polynomials over the field here, to the power of p. So what I can easily do then is write this as a0 plus a1x plus all the way up to am x to the m here, times what we'll have then is a0 plus a1x plus all the way up to am x to the m to the power of p minus 1. And I'm sorry, we've run out of space there. Okay, and now that contradicts the polynomial being irreducible, because both of these things are not going to be units. Because remember, m, that is not, well, this thing here is not going to be a unit. Okay, and the reason is that the polynomial we were initially dealing with, we were assuming that it was irreducible from the start. Okay, so we were assuming it wasn't a constant polynomial, so we had some non-zero coefficients in front of these higher terms, so this will still be a polynomial with some non-zero coefficients in front of actual powers of x, so it won't be a unit in the ring of polynomials over the field. And then when we take it to the power of p minus 1, we will still not have a unit, because we are still working in a ring of polynomials over a field. So when you multiply it, you know, with itself p minus 1 times, you're still you know, the degree is only going to go up, so that's not going to suddenly become something that's a unit. So I have now written my polynomial as two non-units multiplied together, and that of course contradicts it being irreducible. Okay, so there is the proof then of this lemma, that if p of x is irreducible, the derivative of the polynomial cannot be equal to 0, because if we assume that the derivative of the polynomial is equal to 0, then we can prove that it's not irreducible. Okay, so we have now proven that this lemma is true, and because that's going to be true, we can now conclude that whenever the polynomial p of x is irreducible, that the derivative of the polynomial p of x is not equal to 0, and therefore we can conclude that the polynomial p of x and the derivative of p of x are not going to have a common divisor that is not a unit, because we can now say that yes, an associate of p of x is not going to be a divisor of the derivative of p of x, because the degree of the derivative of p of x is strictly less than n, which is the degree of a associate of p of x, and it's not equal to 0, and therefore they are going to be relatively prime, and hence p of x is going to be separable. So we have now proven theorem 1. We'll have a break there, and in the next video we'll turn our attention to theorem 2, which is exactly analogous to theorem 2 for characterizing separable polynomials over a field of characteristic 0.